All right, learning target 2 notes. Today we're going to take a function, find its inverse, and talk about some attributes of that. But first, what about an inverse? What is it? Well, let's use the example of a bank account. You add $5 to your bank account, and then you subtract $5 to your bank account. What's the net result? Nothing, right? It undoes the adding of $5 when you subtract it. The addition and subtraction are inverse relationships. They are inverse operations. So what's the inverse to squaring a number? Root, right. What's the inverse of multiplying? Division. It's the thing that undoes what was done earlier. Okay, so that's what we're trying to find. And we're going to look at relations and functions separately. We're only going to talk about relations. Functions we're going to be practicing and actually assessing. But a relation deals in the finite, and a function deals in the infinite. Have you heard the word finite before? Remember finite? Arithmetic sequences and series, they were finite. They stop. That's all it means. They stop. So a relation, here's an example. A relation is just a finite, a certain number of points that map a domain to a range. So here's a relation R. It maps the value 2, the domain value 2, to the range value 1. So the relation takes 2, maps it to 1. Inverse. Inverse undoes what was just done. The inverse takes that 1 and turns it back into 2. So the inverse relation over here takes the 1, turns it back into 2. It undoes what was just done. All right, had to pause the video there, so I'm not really sure where we were with the discussion, but I know that we talked about 2 mapping to 1 in the original relation, and 1 maps it to 2. It undoes what was just done. All right, moving a little faster. You can also look at an inverse relationship on an XY coordinate plane and make a connection that we're going to use to finish the notes, to go a lot faster, okay? And we'll use a different example. We'll use 5, 2, the ordered pair 5, 2, and its inverse 2, 5, to kind of explore that relation. If you graph 5, 2, it's going to be somewhere in that neighborhood. And if you graph 2, 5, it's going to be somewhere in that neighborhood. And the drawing's a little off, but can you kind of see something about those 2 points? The original point versus its inverse, they're symmetrical. If you folded it on y equals x, they would touch, right? I mean, they're drawn off a little bit, the scale's off, but if you actually drew it to scale, they would touch. What about the point 2,1 and the point 1,2? Would they fold on that line nicely? Would the rest of those points fold on? Yes, they all would. And what that leads us to is this. Finding an inverse is literally just switching the x and the y. And you can see it symmetrical on the picture, that it will be symmetrical about that line, y equals x. So we can go a lot faster now with the notes, now that we've kind of seen that in a relation, moving into functions that are infinite. There's not just a certain number of points, 2, 1, and 1, 2. You can plug in anything into a function, but every number you put in will give you back a y value, and its inverse will undo what was just done. And it'll be symmetrical about the y equals x line. So our first step in finding an inverse is using what we just learned. Switch the x and the y. So f of x represents y. F of x represents y. So when you switch them, this will be x equals 2y plus 1. Literally, you just switched every input and made it the output, and every output made it the input. And that new y that we just wrote there, 2y plus 1, that's the inverse function. I use the word function right now because we don't know if it's a function. We'll have to decide that. But it is the inverse relationship there. So to find our inverse function, we subtract 1. We solve for that new y. X minus 1 equals 2y. Divide by 2. And x minus 1 over 2 equals y. You probably will like that written a little better in slope-intercept form, so I'll go ahead and write it that way too. If you've got an x, which is a 1x divided by 2, you could write it as 1/2 x. And that -1 divided by 2, you could write it as -1/2. So either one's fine. They're the same thing. But that y that we just solved for, this y, gets written as the symbol f -1 of x. You've probably seen that little -1 before. Do you remember where you saw it? The little -1 inverse on your calculator, the sine, the cosine. You remember doing that? What that did back in geometry was it took SOHCAHTOA, like your opposite over hypotenuse for sine, that fraction. When you type inverse sine of that fraction, it gave you the degree of the angle. So the inverse took the degree and made it the output. I don't want to go too deep into geometry, but the inverse always takes your input and makes it your output. All right. So anyways, the inverse function, f -1 of x, is, choose between your favorite. You like it written this way or this way, probably as 1/2 x minus 1/2. But that is the inverse of our original function. All right, so let's test it real quick before, we won't test any of the others, but let's test it to see if it does what it's supposed to do. It's supposed to take your input, and whatever it spits out, it's supposed to take that output and change it back. All right, so let's put a 0 in to the original function and see if when we're done plugging it in, it comes back to us as 0. All right, what do you get when you put a 0 into the original function, 2x plus 1? You get 1, right? So what should happen if we have the right inverse, when we put 1 into it, 0 should come back. All right, so let's see. When I plug in 1/2 times 1, I get 1/2, and I subtract a 1/2 from that, I get 0, right? That's what an inverse will do. It will undo what was just done. All right, so this is the right inverse. We could test as many points as you wanted to test. That one's just easily done mentally with mental math. All right. Now let's have a little sidebar conversation because I don't know if you remember this. Is the inverse a function? Do you remember the vertical line test? Do you remember those words? The vertical line test? So how do you use it? Do you remember? Some of you. Perfect. Perfect. You draw a vertical line anywhere on the graph, and it's only supposed to touch one. So let me give you 2 examples. Here's a parabola, and here is a circle. If you drew a vertical line, would a vertical line ever touch the parabola more than once? Then a parabola, a quadratic, is a function. Could you draw a vertical line that touched the circle more than once? Vertical line that would touch that circle more than once. Here's a vertical line. Does it touch the circle more than once? Then that means the circle is not a function. It's why you can't graph a circle in your calculator. When you go to the y equals menu, you can't graph a circle because it's not a function. All right, so that's the vertical line test. So is our inverse, which is right here, a function? Well, what's that a picture of? 1/2 x minus 1/2. The line, right? A slope-intercept line. So would a line that has a slope 1/2 and y-intercept -1/2 pass the vertical line test? Yeah, so it's a function, and we might need to go ahead and graph this before you can say for sure. So let's do that. Honestly, you should be able to graph these without using the calculator at all, but we will. All right, you kind of see a remnants of one of our old problems there. All right, so graphing. First, in the y1, we'll graph the original. So the original function was 2x plus 1. 2x plus 1. In y2, we'll graph y equals x because I want to see that it's symmetrical, see that it folds nicely. So I'll graph y equals x. And then in the third, we'll graph our inverse. And the inverse function was 1/2 x minus 1/2. So parentheses 1/2 x minus parentheses 1/2. When I hit graph, it's going to graph 3 lines. The first one's the original, the second one's y equals x, and the third one's the inverse. So here it goes. There's the original. There's y equals x, and there's the inverse. Could you fold that picture on y equals x and get the same thing on both sides? That's symmetry, which means it's a good sign you found the right inverse, okay? So when I say sketch the graph, that doesn't mean graph nice, perfect points. It just means draw that picture in general. So the original, I'll use blue. The original had a slope of 1 and or slope of 2 and y-intercept of 1. So something like that. The inverse had a y-intercept of -1/2 and a slope of 1/2. So it would look something like that. And then label that the inverse. Label the blue one f of x. And you can see the symmetry on your own paper, right? Good so far? Now, it's probably a little easier now to see. Look at the red line that we just drew. Is there a vertical line that would ever touch that red line more than once? Then it passes the vertical line test. It's a function. The answer is yes. All right, last part, domain and range. Sorry about that. The domain and the range. What's the domain? And you won't see what you need to see in this linear example. You'll see it in the quadratics on the back. What's the domain of your original line? What can you plug into 2x plus 1? Yeah, anything. What do you get out of it when you plug those in? What's the range? All real numbers. What about your inverse? What was its domain? What can you plug into that line? All real numbers. And what comes back? All real numbers. So again, you won't see what you need to here. You'll see it on the back. So we have 2 more examples, quadratics. 2 more examples. And they are quadratics. I'll pause the video for just a second and just give you a chance to try the first step on example 2a. Well, the first step, switch the x and the y. When you change that to x and that to y, the y that you just wrote down is the inverse. You just have to get it by itself. So quick little sidebar before we get to it. What would you do in this situation? Just a reminder. When you take the square root of both sides, x equals what? X doesn't equal 5. It equals plus or minus 5, right? You got 2 options, a 5 or a -5 that could have made that 25. So we're going to use that right here. When you're getting the y by itself, you add 1, and x plus 1 equals y squared, and then we take the square root of both sides, and we have to have the positive and negative answer. So plus or minus the square root of x plus 1 equals y. The y that you wrote right here, that is the inverse function. I use that word, probably shouldn't, but it is the inverse of the original function. It's, spoiler alert, it's not a function, okay? The inverse is not a function, but we'll see that when we graph. Here's your first, we'll use the calculator to help us out on this one. We shouldn't need the calculator to graph x squared minus 1. Do you remember what minus 1 would do to that quadratic? X squared minus 1, how would it move? Down 1. The minus 1 being after the x squared would go down 1. So we probably shouldn't need to see it, but this will confirm x squared minus 1 shifted down 1. So over here, our original function looks something like that. And if you remember what we just talked about on the front side, about the symmetry, you could probably go ahead and graph the red one, the inverse. Because all you're going to do is take that blue parabola and fold it. Fold it at the y equals x line. And that's your new inverse picture. But we'll let the calculator help us out. And this, again, is kind of a sign that you are looking at an inverse that's not a function. It's going to take two lines to graph this. There's no plus or minus button. There's no plus or minus button to type right here. So the only way to graph the inverse is to graph the positive square root of x plus 1 into y3 and graph the negative square root of x plus 1 into y4. So if it takes two y values to graph the inverse is not going to be a function. But just so we can see what it looks like, there's the inverse. A kind of sideways parabola, if you will, right? A sideways. And wouldn't that be the picture that you get when you flip that blue parabola? So when I grade these, when I'm grading your homework, I'm sorry, not your homework, but your quiz, the first thing I'm going to look at on this picture is, can you fold the picture that you drew on the dotted line? Is there symmetry? Because there should be, right? So I'll be looking for the symmetry, and I'll also be looking, is your original function, is it in the general vicinity of where it should be? But I'm not looking for little hash marks of 1, 2, 3, 4, 5 and graphing it exactly, just a sketch. Okay. All right. And again, was it a function? It's not a function. No, because if you drew a vertical line right there, it would cross the inverse twice. So no, it's not a function. All right, and domain and range. This is where you finally get to see the big picture, okay? We've talked a lot about domain and range, and what we are about to see happen is what's going to make target 3 and 5 so easy. So easy. But it's conceptual. And yes, I could have started this whole lesson with, all you got to do is switch x and y, and you're good. We could have done that, yes. But then you wouldn't have the deep understanding, the real meaning of why and what's going on, okay? But anyways, what's the domain of your original quadratic? What's the domain of that blue quadratic? What can you plug in for x? All real numbers. You got it. What's the range of that quadratic? Y is greater than or equal to negative 1. All right, here's a little reminder. You're just, in the inverse, switching x's and y's. You're just switching x's and y's. What's the domain of your inverse? What can you plug into that square root of x plus 1? Greater than or equal to negative 1. Your x value has to be greater than or equal to negative 1. Very similar to the range of your original, right? What's the range of the inverse? Will that sideways parabola go up forever and down forever? Then the range is all real numbers, just like the domain of your original. So what happened there? See some of your fingers switch. They just switched. Your x's and y's switched. Your domain and your range switched. All right, I'm going to pause the video and let you try the last one. It's a quadratic. Try the last one. Let me get you guys off on the right foot. I've seen you switch that. You're switching the x and the y, right? How are you going to get to that y? How are you going to get that y that's in the parentheses by itself? Well, you got to get rid of the plus 3, the squared, and the minus 1. But there's an order you have to do that. First, you have to get rid of that minus 1. Add the 1 to the right side, or to the left side. And when you do, you've now got the squared part by itself. So how do you get rid of that squared part? You take the square root. Take the square root of both sides. The y plus 3 comes out, and when you take the square root, you have a positive and a negative option that would have made that perfect square. And then the final step, subtract the 3. So when you write it, the square root of x plus 1 minus 3, the minus 3 is after the square root. It's after the square root. And that y is your inverse. And I use the word, it's your inverse. It's not necessarily a function, okay, until you decide if it is a function. All right, and I'll pause it now again, and you can try to finish the sketch, the domain, the range, and is it a function? And I'm going to repeat what I just said for the video's sake because I want the video to have this. But you don't need that calculator at all because the original function, if it says x plus 3 and minus 1 there, it's going to move the parabola down 1 and left 3. So that would be right here, roughly. Your original parabola looks like this. And if you're understanding the concept of inverse and how it's symmetrical about y equals x, you know where the new picture is. Fold that paper on that dotted line, pretend it's wet paint and it's red paint. Where would it leave an impression? It would leave an impression down here. If you're conceptually understanding the process, you don't need the calculator at all. Now, we're welcome, again, to use it, but in using it, you have to type in quite a bit. X plus 3 squared minus 1. We'll leave the y equals x there. Probably should have left those there. But then we'll have to graph the square root of x plus 1, right arrow minus 3, and the square root of the negative square root of x plus 1, right arrow minus 3. So it actually takes a lot longer to use the calculator to get this picture than it would if we just understood it conceptually. That's the point of target 3 and target 5 when we get there. It takes longer to use the calculator than it will if you really understand what's going on. Trust me, okay? But that picture confirms what we got, right? All right, so what's the last two answers? Is the inverse a function? Does it pass the vertical line test? No. And then what's the domain and range? And I'll do them in a different order this time. What's the domain of the original? What's the domain of that original quadratic? All real numbers. All right, now I'm going to change the question. What's the range? What's the range of the inverse? What's the range of the inverse? All real numbers. Switch, right? What's the range of the original function? What's the range of that blue quadratic? Y is greater than or equal to -1. So what's the domain of your inverse? X is greater than or equal to -1, and you're kind of seeing the conceptual connection, right? Okay. I think I'm going to like the homework too after all. Let me go ahead and stop the video.